All right, chapter 6, electronic structure of atoms. Okay, electromagnetic spectrum and wave-like properties. Waves here, like electromagnetic radiation moves as waves through space at the speed of light. The speed of light is 3.00 times 10^8 meters per second. Okay, so in wavelength, so you have this electromagnetic radiation, right? It moves as waves, and the distance between the corresponding points, like this wave here, we call the wavelength. And here, for example, if you compare letter A, this wavelength here with this, the letter A has higher wavelength than letter B. The number of waves passing in a given point per unit is the unit of time is the frequency. For example, here, right? How many times the wave is passing here? For example, 1, 2, 3, 4, 5. The letter B, 1, 2, 3, 4, 6. So this is the number of times the number of waves passing a given point. And the unit of time will be in second, will be per second or hertz. The unit for frequency will be second to the -1 or hertz. So you can see, right? The letter A have a larger wavelength and shorter frequency compared with this letter B. Letter B will have a shorter wavelength and higher frequency, right? You can see passing. The numbers of times the wave is passing here is higher than what you have here. What that means? When frequency increases, wavelength decreases, right? For example, here you have electromagnetic radiation. When the wavelength will be in meters here, when the wavelength increases, frequency is decreasing. So you have here all these radiations from gamma rays to radio frequency, and each one will have a region of wavelength and frequency. For example, here, the visible region, that the visible that we can see, the humans you can see, is between 400 nanometers to 750 nanometers. So the number here from 400 to 50 is increasing, and the frequency is decreasing. So you can see here nanometers, right? So the questions usually give the unit, the frequency, and the wavelength in nanometers. Each 1 nanometers is equal 10 to the -9 meters. So we usually need to do this conversion here. Why need to go from nanometers to meters? Because in speed of light, the unit of speed of light constant, the speed of light number here is 3 times 0 times 10 to the 8 meters per second. And how can you calculate the speed of light is wavelength times frequency? That means if we arrange this formula to calculate frequency will be speed of light divided by frequency. So speed of light divided by wavelength. So frequency is speed of light, that's meters per second, divided by wavelength, it will be in meters. That's why you needed everything in the same unit. Cancel meters with meters, so your unit here for frequency will be second to the -1. Okay. For example, here we have this problem, practice problem 1. Which wave has the highest wavelength? It's how you can see here. So the distance between these 2 points for the number 1, right, is larger than for the second wave here. This one is shorter than this first one. And the third one is shorter than all between these three radiations. That it means the number one is one that it has a higher wavelength. Right? For example, here, if you compare the spectrum here, the region that it has higher wavelength, the visible region that it has higher wavelength is the red light region here. Okay, all right. Then press problem 2. A laser used in eye surgery to fuse detached retinas produces radiation and with an wavelength of 640 nanometers. So calculate the frequency of this radiation. What's the formula for frequency? Speed of light divided by wavelength. And wavelength needs to be in meters. So the question gives to us in nanometers. So let's do the conversion here. Right, each 1 nanometer is 1 times 10 to the minus 9 meters. So take this 640 nanometers that was given here, multiplied by the conversion factor here. So you know that each 1 nanometer, you have it 10 to the minus 9 meter, right? Cancel, cancel. So your number in meters will be 6.0 times 10 to the minus 9. Oh, sorry, to the minus 7 in meters. Another way you can like plug directly here. You can plug like 6.40 times 10 to the minus 9. Yeah. That's going to be this number anyway here. Another way is to plug directly the wavelength conversion from nanometers to meters. Will be the same thing here, equivalent. Right? So then let's divide the speed of light divided by the wavelength in meters. Okay, right? Attention here. So some calculators will not understand if you don't type the parentheses. So take the number in the numerator. Don't need the parentheses on the first one, but the one on the bottom. So type this number, then divide by, open parentheses, type this number, and then close the parentheses, and then equal to get this number here. So if you don't get this number, because you are not typing correctly in your calculator, right? So frequency here should get this number here. The unit is per second, right? Okay. So properties not explained by waves, but rather by particles. So have here intro to wave particle duality. The emission of light from hot objects, black body radiation. Planck's constant assume that energy comes in packs. Gonna be packs that are gonna be your quanta. The emission of electrons from metal surfaces on which light is shone would be the photoelectric effect. Okay, then Einstein solved it using Planck's concept to conclude that energy is proportional to frequency. So that means when frequency increases, energy increases, right? When the packet of set energy amount will be the light quanta. Okay, so using Planck's concept, you have then Planck's constant, the W here in the energy. Energy is Planck's constant times frequency, and Planck's constant is this value here in unit is joules times seconds. So 6.6 times 6.626 times 10 to the minus 34 joule seconds will be your Planck's constant. So will be given to you. So then, okay, calculate the energy of one photon of yellow light that it has a wavelength of 589 nanometers. Okay, what's the formula to calculate energy? Here's one. Energy is Planck's constant times frequency. Okay, so that energy, we have a Planck's constant right here, times your frequency. How can you calculate frequency? So this from the previous page, right? Frequency is speed of light divided by wavelength in meters. So the wavelength given here was in nanometer. So you can just multiply directly here to the -9 to convert it from nanometers to meters. So in other words here, frequency is speed of light, that is 3 times 10 to the 8 meters per second, divided by the wavelength in meters. Again, make sure you type the parentheses. Some calculators will not understand if you don't type the parentheses. Then this frequency here, you should get this number, right? Okay, now let's go back to calculate energy, right? This is the frequency here, this value that was calculated separately here. All right. Okay, so this problem 4. A laser emits light that it has a frequency of 4.69 times 10 to the 14th per second. What's the energy of one photon of this radiation? So here, right, energy is Planck's constant times frequency. Planck's constant we have right here. Let's just plug, right? 6.626 times 10 to the minus 34 joules second. That is the Planck's constant, right? Times frequency. The frequency was given. That means you do not need to calculate, like question 3 did not give the frequency, but the question gave wavelength. And how calculate the wavelength? Oh, sorry, how to use the frequency? To calculate frequency, we got speed of light divided by the wavelength in meters, right? So the question here, but the question 4 is easier just because this question already gave us the frequency, 4.69 times 10 to the 14, here, 7 to the -1. So cancel out seconds with seconds. We multiply this by this, your energy should be 3.11 times 10 to the -19 joules. By the way, number 3 should be, when you multiply this by this, you should get 3.37 times 10 to the -19 joules. All right, okay. So now we have emission of electronically excited gas atoms. So have here emission spectrum. So each atom will have a different spectrum. For example, here, I was in hydrogen, you have 1, 2, 3, 4 lines here. And each one is different wavelength, right? And the neon, you'll have a bunch here. So each spectrum here is like the fingerprint of each atom, because we also relate to the each electronic configuration when the gas atoms here, they excited, we show this spectrum here, emission spectrum, when energy is emitted, right? Okay, so then Balmer discovered a simple formula relating the four lines of two integers. So, for example, to calculate what was the wavelength when the electron jumped from energy level 1 to 2, for example, initial and the final, then you have this formula here, like here. And 1 is going to be your initial, the N here is for energy level. And, for example, in energy level, the initial and the final energy level. So you can use this formula to calculate what was the energy transition from when the electron jumped or returned. So here. And then right back at advanced Balmer's formula and at the R8 is a constant. R8 is called Rydberg constant. They have this number here to the -1. Oh, in Bohr model, it says on orbits for Bohr model. Oh, by the way, in the beginning of chapter 2, we saw different atoms model, right? The first one until they accept the current accept one. Bohr model is not the last one accepted, but we still need to use Bohr model to explain about electron transition, the electron emission, like the energy emission, the emission or absorbing energy. We're going to use talking about still about orbits. So all orbits of certain radii corresponding to a specific energy are permitted from the electron in a hydrogen atom. So energy of an electron is quantized here. So when the electron jumps, for example, energy level 1 to 2, the transition of electron from a lower to a higher energy level will have absorption of energy from lower to a higher. Then when the electron jumped from a higher to a lower, you have energy, releasing energy. The transition of an electron from a higher to a lower energy states releases energy. From lower to a higher, we have absorption, right? And higher to a lower, you have emission or releasing energy. Emission. So electrons in the lowest energy are in the ground state. Right, so energy can be emitted or absorbed, like I showed here, by the electron only as the electron changes from one energy level, energy state to another. This energy is emitted or should be or here or absorbed. As a photon has energy, right? So in the previous question there, energy is Planck's constant times frequency. But how can we calculate the energy change, like in the when electron transition here? So electrons in the lowest energy level we call the ground state, and any energy higher is called excited state. For example, here, right? The first one, electrons right here, the ground state, and then jumped here to the second. We have right here would be the ground state, and this one would be the excited state, right? So since orbit has a specific value compared to RH, the transitions from one energy level to another the energy level can be calculated using this formula here. This is another also Rydberg constant here. To calculate the energy the energy that was absorbed or released when the electron like change the energy levels. So values of transition, what that means here. So N positive delta E means energy is absorbed. That's a photon is absorbed in this instance here. So delta E is positive. This happens when if the final energy level is greater than the initial, right? So your delta E will be positive here. And then a negative delta E means energy is released. So a photon is emitted in this instance. This happens when the final energy is smaller than the initial. Here delta E should to be -1. Okay. Okay. So let's see this problem 6 here. Problem 6. Indicate like if each of the following electronic transitions emits energy or requires the absorption of energy. Like here, from 3 to 1, right? So 3 is the initial and the final is 1. What you have in here? Which one is higher, the initial or the final? So here the final number, right, is smaller than the initial, right? It means so when the final is smaller than the initial, you have emission, right here. When the final is smaller than the initial, you have the emission. Emitted. A photon is emitted here. Right, in the next one. So the initial here, number 2, and the final is number 4. Right, it's like this one is 1, 2, 3, 4. So energy level 1, 2, 3, 4. So this electron here jumped. The electronic transition here was from number 2 to 4. So when you go from a lower to a higher energy level, is have absorption. Absorption, right? So from lower to a higher, absorption, right? You know, when you have from a higher to a low energy level, have it's releasing or emitting, right, energy here, releasing. Right? Okay. By the way, I think I have a question like this in the review, number exam 2 review. Okay. So limitation of Bohr model. So important ideas. They're correlated with current atomic model. So electrons exist only in certain discrete energy level, which are described by Bohr's theory. And energy is involved in the transition of an electron from one level to another. So here, energy. So again, we are using Bohr model here just to explain the transitions, right? The electronic transitions from emitting or absorbing energy. The latest Bohr model is not the latest atomic model is not the Bohr's model. The Bohr's model was saying that the electrons are in perfect orbits, and this is not true, right? It's not that the electrons, they are in electron clouds, and it's not in perfect orbits. And here, use this idea just to explain about the transition. You go back to Bohr's model just to explain about the electron jumping or returning to the original, to the ground state. All right? Okay. So let's see. So the next is quantum mechanic model. So let's talk about the electron cloud. So Stronger developed a mathematical treatment in which both the wave and particle nature of matter could be incorporated. So this is known as quantum mechanics. So the focal point of this theory, there are areas of atoms that demonstrate a high probability of where to find electron in a given time. Okay, so and then it's like the idea, quantum numbers is like the GPS to find the electron. Here. Focal point of this theory is there are areas in atoms that demonstrate high probability where the electron is likely to be found. And right here, we are going to learn about quantum numbers. Quantum numbers they are like the GPS to find where we can find the electron. But before we go to quantum numbers, I need to show about electronic configurations that you have seen in high school, but I need to review about electronic configuration first. So I'm going to stop here, and then I'm going to show only about electronic configuration. Then I'll go back to chapter here.